Hello, my name is Kyriakou. I'm a postdoctoral researcher at the University of Cyprus. I'm working with Dr. Symeon Christodoulou, and we will present you a payment rating system based on machine learning. This work is partially funded by the European Regional Development Fund and the Republic of Cyprus through the Cyprus Research and Technology Foundation. This is our presentation outline. First, we will talk about our research goals. Secondly, about the state of knowledge concerning defect detection. Then we will discuss about the payment rating systems that we develop. And finally, some conclusions and future work. Our research investigates the development of a GIS-based pavement monitoring system for the evaluation of the pavement condition based on smartphones, onboard diagnostic devices, statistical analysis, and machine learning. Our research goals is the development of a low-cost detection of surface anomalies, the development of a low-cost method based on smartphones and machine learning techniques, the development of an evaluation support system for roadway pavement management, and finally, the development of a GIS pavement monitoring system for detecting and classifying pavement surface anomalies. This is our expected output. We expect that a vehicle, while it's moving, it will detect the right roadway surface anomaly. It will classify the surface anomaly into the right category and also report the geographic coordinates of the surface anomaly. Now, the current collection practice using imaging technologies is able to detect all pavement surface distress types, but the evaluation of pavement surface is conducted 1 or 2 times per year because of their high cost. This is an example of a specialized survey vehicle. In the pavement management system process, very important are the stages related to data collection process, the classification and evaluation of pavement defects, and the spatial mapping of pavement condition. These stages have been cited by many researchers with their work focused on low-cost defect detection. Concerning limitation of vision-based methods, they need steps of noise filtering and background illumination correction. They rely on 3D surface reconstruction, which comes along with a high equipment and computation cost. And finally, they require large storage space and expensive computation for imaging processing. Concerning the vibration-based method limitations, they depend on exactly how the road surface anomaly is hit by the tire. Despite the hardware differences, they show that pothole detection is possible. And finally, a speed dependence removal approach must be utilized, especially when there is a sudden stop. Our pavement monitoring system is vibration-based. It highlights the use of gyroscope values, roll and pinch values, in order to avoid speed dependence and false indication when there is a sudden motion. It monitors 5 roadways anomalies instead of 2 or 3 of existing systems. And the goal of the research pavement monitoring system is the development of a GIS pavement monitoring system. The study presented explores the use of data collected by sensors from smartphones OBD devices, where vehicles are in movement for the detection of roadways anomalies. The smartphone-based data collection is complemented with robust regression analysis and unsupervised machine learning classification models. 31 factors were used for the detection of roadway surface anomalies, which were statistically reduced to 4. Why we use vehicles? Because one of the most important indicators for road quality is the road surface condition, which is defined by the anomalies in the pavement surface that have an effect on the ride quality of a vehicle. Road anomalies can damage vehicles, cause unpleasant driving, and sometimes be the reason for traffic accidents. So, by detecting roadway anomalies on the surface can contribute to surveying road surface quality. Why we use smartphones? Because of the fast and intense development of smartphones in current years. Smartphones come with a large range of built-in sensors such as accelerometers and gyroscope. Why we use OBD? Because vehicle system data can be collected through OBD devices, and this combination allows us to monitor many variables, including forward lateral acceleration and vertical acceleration, vehicle roads, and vehicle pitch. Now, concerning our road surface anomalies that we are trying to detect, according to the Federal Highway Administration, there are longitudinal, transverse, blocked, and alligator cracks. Rutting is a displacement of material creating channels in wheel paths. Raveling is a progressive loss of pavement material. Patches are original surface repair with new asphalt material. Potholes are holes or loss of pavement material. Concerning our system components, we utilize smartphone and vehicle data, statistical analysis, and supervised machine learning techniques, and we managed to develop a 5-class rating pavement surface system. We cover a 10-kilometer distance. We use an SUV vehicle and an Android smartphone, and we collect our data in an actual sampling rate of 10 Hertz, and we utilize K-medoids clustering. This is a flowchart of our proposed system. We collect data from smartphones and vehicles. We perform statistical analysis. We utilize unsupervised machine learning techniques, and we develop a pavement surface rating system. The car was fitted with a smartphone with its GPS, gyroscope, and accelerometers activated. Also, its video camera was active in order to visually verify the existence of roadway anomaly. The smartphone was fitted with dash command application for recording sensor readings, and furthermore, vehicle system data could be relayed through the OBD reader. The sensors data is taken at an interval of 0.1 seconds, and further to unidimensional data, application also reports on the smartphone's roll and pitch values. The roll relates to car acceleration differential between its left and right front wheels, while the pitch relates to a car acceleration differential between its front and rear wheel. In tandem, roll and pitch values indicate how an object is off balance, in this case, the car. The physics investigation included the collection of sensor data for 31 parameters, and the number of regression techniques investigated the statistical significance of the factors. These are the most important variables concerning our system, our data collected. Then we utilize feature extraction, which is a process of dimensionality reduction by which an initial set of raw data is reduced to more manageable groups for processing. We utilize several time domain features as data aggregators. Then the data were fed into an unsupervised machine learning algorithm for clustering analysis. Clustering analysis is a classification process in which data are grouped into groups of similar features. Then we utilize k-means clustering. The objective of k-means clustering is to minimize the Euclidean sums of square deviation of objects from the cluster mean, and as a ground truth for verifying the method detection accuracy for speed bumps, patches, and potholes, the smartphone recorder video was used. Then we fed our data into k-means clustering algorithm concerning the k-methods clustering procedure. The cost of each selection is calculated, and in contrast to the k-means algorithm, the k-methods method classifies 5 categories correctly concerning our data set and our problem. K-methods in general is more robust and faster than the k-means algorithm. This is our k-methods rating system. In category 1, we don't have any visible distresses. In category 2, we have longitudinal and transverse cracks. In category 3, we have severe raveling and block cracking. In category 4, we can detect patches and occasionally potholes. And in category 5, we have mainly potholes and some speed bumps developed under no regulations. One of our research goals is the development of a spatial decision support system where the results of the unsupervised machine learning analysis, in our case the k-methods clustering scores, will be mapped spatially, indicated areas of concern, and further generated heat maps can be utilized by the agencies to prioritize their regulations and budgetary actions. This is an example of the spatial condition assessment mapping that we are trying to build. This example includes classes of 4 and 5. To conclude, the paper describes a methodology based on low-cost devices and unsupervised machine learning methods. Our motivation was to create a system that automatically assesses the quality of the payment based on accelerometers, gyroscope, and clustered methods, and map the existence of roadways anomalies. Our methodology is low cost and highly scalable as the number of smartphones users increase day by day. It removes the need to deploy spatial sensors and expensive specialized vehicles, and it does not require any expertise in payment condition assessment. The applied methodology is obtainable, low cost and accurate, and can be utilized in crowdsourced applications leading to payment management system. It's currently field tested with larger datasets and a higher number of roadway defects types, with links created to GIS mapping and database management system for the use of the proposed methodology in payment management system. Thank you for your attention, and if you have any questions, I will be happy to answer them.